Hello, good morning. In this video, we are going to discuss some of the concepts and definitions for geometrical significance of velocity and acceleration, scalar and vector point function, limits and continuity. First one is geometrical significance of velocity and acceleration. Now, the velocity. Here there is a diagram and I'm having a point O and a point P and a point Q, and OP is the vector denoted by R. And if I move delta R, if I change the position of the point P to the point Q with delta R, I will get another position vector as R plus delta R, right? So let time be the scalar variable, and that is equal to t. Displacement of the point P in time delta t will be, yes, that displacement will be this PQ vector, which is equal to delta R. This is your displacement in time delta t, right? So therefore, average velocity in time delta t will be given by, yes, rate of change of displacement with respect to the time. Change in the displacement with respect to the time. So if we proceed to the limits, then when delta t tends to 0, which means if this point Q tends to this point P, obviously because delta R is the vector, it is the displacement in time delta t. If delta t is tending to 0, when Q is tending to P, then the chord PQ is tangent at P. So this will be as this chord, which is now a tangent at P point, right? And we get velocity at point P, which is equal to limit, because we have tending delta t to 0, and this is change in displacement with respect to the time, and hence we get velocity v vector that is equal to rate of change of displacement with respect to the time. So where this v represents the velocity of the particle after time t, that is the rate of change of displacement with respect to time. Similarly is the case for the acceleration. Let change in velocity in time delta t will be, we are taking the change in velocity, then we write delta v. This delta v represents the change in velocity. Then average acceleration in time delta t will be, yes, change in velocity in time delta t, change in time delta t. So proceeding to the limits, when this delta t tending to 0 like before, that means when the point Q is tending to P, we get limit delta t tends to 0 delta v over delta t. This is equal to, yes, dv over dt. So this is your, we denote this as your A vector, that is your acceleration, which is given by dv by dt, where A vector represents the acceleration of the particle after time t and the rate of change of velocity with respect to time. So acceleration is also denoted as rate of change of velocity with respect to this time t. Fine? Alright. Next, scalar point function. Suppose I am having the region R. Let R be any region of the space, and if corresponding to each point P of the region, suppose I have taken this point 1P, and it's talking about corresponding to each point P, that means we have to consider for every point P in the region. So for every point P, there corresponds a scalar denoted by phi p, then this phi is said to be a scalar point function. For example, temperature at any point of a body occupying a certain region is scalar point function defined for the region. Then is vector point function. Let R be any region of the space. Suppose this is your region again, R. And if corresponding to each point P, if this is your point P, but I have to consider for every point P, there corresponds a vector denoted by Fp. Then this vector F is a vector point function. For example, consider a body in motion. Suppose this is a ball which is in motion. At any time t, if vector Fp denotes the velocity of the particle at a point P, then F vector is a vector point function defined for the region occupied by the body. You can take this as your region occupied by this body. So this F vector denotes the velocity of the body at the point P, right? Then is the definition for the limits and continuity. The first definition for scalar point function. A scalar point function phi p is tending to limit L when this P, the point inside the sphere, suppose this is your sphere and there are so many points P. If this P is tending to A is your given point which is centered point. If to every pre-assigned epsilon positive there corresponds delta positive such that phi p minus L mod is strictly less than epsilon for all P inside sphere except the possibly for point A. Now this will be for all the points in the sphere except this point A, right? Then we say that this scalar point function phi p is tending to limit L whenever any point from the sphere is tending to this point A, right? So for that we have limit p tending to A, phi of p is equal to L, right? Where L is your limit. Similarly, we can write the definition for the vector point function. A vector point function fp is tending to L when p is tending to A to every pre-assigned epsilon positive. There exists delta positive such that mod of fp minus L is strictly less than epsilon for all p within the sphere except possibly for a point A, because p is tending to your point given point A. So limit p tending to A, f of p vector is equal to L. We write this. Then is there are two remarks given over here which are very important. First for the scalar point function, then we read the remark for the vector point function. A scalar point function phi p is said to be continuous at a point A if limit p tends to A, phi of p is equal to phi of A. Also, a scalar point function is said to be continuous if it is continuous at every point of its region of definition. So it has to be continuous at every point, right? Not at a point P only, but for every point in the sphere, in the region. Similarly, a vector point function fp is said to be continuous at a point A if limit p tends to A, f of p is equal to phi of A. This is your scalar function. Also, it is continuous if it is continuous at every point of its region of its definitions, right? So here ends up the video with these definitions. Next time we are going to start the directional derivatives and the Cartesian representation of point functions and their directional derivatives.